Hi guys, welcome back to Study Links, and this is the series Physics 101 in which we're covering the complete O-level physics syllabus. And beginning with this chapter Kinematics, we're not doing the physical quantities chapter because I think that it is too easy and I think it does not require any video. You have to simply memorize the units and simple measuring instruments accuracies. So without any further ado, let's start with the topic kinematics. Now kinematics is basically studying motion of an object without reference to the forces causing it. So here we're going to be talking about speed, velocity, distance and displacements. And before getting into the detail of the topic, I would like to talk about vector and scalar quantities as they are very important in this chapter. Now, a vector quantity is a physical quantity which expresses both magnitude and direction. So, they do not only tell you about the magnitude of physical quantity but also the direction. And a scalar quantity is a quantity which expresses only magnitude and not direction. Now, the next quantities we are going to discuss, some of them will be vectors and some of them will be scalars. And let us begin with distance. Now, a distance is basically the length covered by a moving object and is a scalar quantity. So, direction is not written with it and it only tells you about the magnitude of the length it has covered. For example, if a body has moved from point A to point B, it will, and the distance is 100 meter. This will be the distance covered by that body. Similarly, if the body is moves to from point A to point B in a non-linear path, for example, it forms like this random path, and then again the length covered by the object would be the distance. So linear was 100, so it could be even like 200, still it would be the distance. And distance is actually measured in meters, kilometers, feet, but the SI unit is meter. And this brings us to the next quantity, which is displacement. Now, displacement is the linear distance between the initial and final position of a moving body. So, and is a vector quantity. It means that it also tells about the direction of the moving body, like it has moved 500 meters to north or south. For example, if a body has started from point P and is going to point Q, and it has covered, like it has moved in point, it went to point L and point M, then went to point Q. Now this whole, the length of the whole path, let's say, was 500 meters, but this would be the distance. And the displacement is the linear distance between the initial position and the final position of a moving body. So the displacement would be this straight line from point P to Q. This would be the displacement. Now let us look at another example. A cyclist starts from point A, goes 400 meters straight, and then comes back where it originally started. Now, the distance between the this point and let's say this point Q is 400 meters. What would be the distance and displacement? The distance here would be 800 meters, as the total length of the path which the cyclists have covered is double the path of A to Q, which is 400 meters. So the distance would be 800 meters. First goes A to Q, that's 4, and then comes back from Q to A, that is again 400 meters. So the distance would be 800 meters. Now the question is, what would be the displacement? The displacement here would be 0. Why is that? Because when we talk about displacement, we said that it is basically the linear distance from the initial and final position, and as the initial and final position is the same, so displacement will be 0 meters. And this brings us to the next quantity, which is speed. Now the speed is the quantity used to describe how fast or slow an object is moving. And what this tells us, it basically tells us the rate at which an object is covering distance. We could alternatively say k distance covered per unit time. So let's say an object from point A is moving to point B, and the distance between A to B is, let's say, 40 meters, and the time the time it took for the object to move from point A to B was, let's say, 10 seconds. Now what would be the speed? The speed is calculated, the total distance was 40 meters and the time taken was 10 seconds. So distance over time is 4 meter per second. So the speed was 4 meter per second. And so speed is calculated using the formula speed is equal to distance over time. Now, there are circumstances when an object does not travel at a constant speed. Its speed increases and then it may move at constant speed for a while and then its speed may decrease. For those conditions, we use the term average speed. So if a train moves from point P to Q and the distance is, let's say, 1000 meters, and it completes it in around, let's say, 30 seconds, then the speed would be speed then, and we do not, and there were times when the speed was increasing, the speed was constant, and the speed was decreasing. So its speed at different instants was different. So we now can calculate from this time and distance the average speed, and hence the average speed would be average speed is equal to total distance over total time taken. So which in this case would be 1000 divided by 30. And this is about the speed, and the SI unit for speed is meters per second, and it is actually a scalar quantity. And this brings us to our next quantity, which is actually velocity. Now velocity is actually the same as speed except that it has direction, so it is a vector quantity. and its definition is similar to that of the speed. We write it as displacement covered per unit time. Its formula is same as that of the speed, which is v is equal to d over t, distance over time. And that is it for the velocity. And now comes another quantity, which is acceleration. Now acceleration is basically the rate of change of velocity. That is, acceleration is equal to change in velocity over time. And now make sure that you do not confuse this velocity with speed. It is rate of change of velocity and not speed. There are times when the speed is remaining constant, but the body is actually accelerating. And how is that? Because its velocity is changing. How is the velocity changing if its speed is constant? Because its direction is changing. So for example, if a body is moving in a circular path, let's say, and its speed is constant, still it is accelerating, because you know that its direction is constantly changing, and therefore it is accelerating. Velocity is changing because of direction and is accelerating. There is the term deceleration used. Deceleration is basically the negative acceleration. If the velocity is increasing, we say that the body is accelerating, and if the velocity is decreasing, we say that the body is decelerating. Now let us calculate acceleration of a simple example here. Let's say an object A was moving and its speed increased from 5 meters per second, which means initial speed, which is represented by u, is equal to 5 meters per second, and accelerated to 10 meters per second, which is the final speed. So this is represented by v, which is equal to 10 meters per second in a time of 2 seconds. So the time taken for the object to reach 10 meters per second from 5 meters per second is actually 2 seconds. So now they're asking us to calculate acceleration. What is acceleration? Now, as we talked earlier, acceleration is basically change in velocity over time. So the change in velocity over here is final velocity minus initial velocity, that is 10 minus 5 divided by 2, that is 2.5 meters per second square. We have also come to know the unit for the acceleration, meters per second square. Now let's look at another example. Now they are asking us to calculate acceleration. Now acceleration would again calculate change in velocity over time. Now final velocity minus initial velocity, that is 30 minus 50 divided by time, which is 5, and the answer would be, we would get, is actually negative 4 meters per second square. Now what does this negative mean? This negative mean deceleration. So every second the speed of the object was decreasing by 4 meter per second. So the acceleration is negative 4 meter per second squared. So either you can say the acceleration is negative 4 meter per second square, or alternatively you can say that the deceleration is 4 meter per second. This brings us to the next part of this chapter, which are the graphs. We're going to be discussing two graphs over here. one is actually the uh, displacement time graph and the other is velocity time graph, and we will be beginning with the displacement time graph. Now, as you can see, the displacement is labeled on the y-axis while time is on the x-axis. And let us quickly here sketch a line. Now, this is a line with a constant gradient, and if you look closely, the gradient of this line would be equal to change in displacement over time. Now, as it is change in y or change in x, and same thing change in displacement or change in time, and when we discussed velocity, we said that velocity is equal to displacement over time. So we can say that gradient over here is actually representing velocity. So this thing has to be noted over here, that gradient of a displacement time graph represents velocity. So as you can see, the gradient is constant throughout the graph. Here we can say that velocity is constant. So velocity does not change throughout this graph. Now let us look at another example of a graph. Now here I have sketched a straight horizontal line, and a straight horizontal line has zero gradient as there is no change in the quantity or y-axis. So the change is zero, so the gradient would be zero, and as the gradient is equal to velocity, so we can say that over here velocity is zero. Now if you look over here, the gradient of the line is constantly increasing. Like if you see here, the gradient was something like this. If you draw a tangent over here, and if you see here, the tangent over here is like this, and it is getting steeper, and as it is getting steeper, it means that the gradient is increasing, and the gradient is velocity, so we can say that over here velocity is increasing, which basically means that it is accelerating. Now let's move on to the next example. In this sketch you can see that the gradient of the curve is decreasing. Like you see over here, gradient is getting less steep. I know that lines are not perfect, but uh, I'm drawing it with hand, so sorry for that. But here you can see that the gradient of the line is constantly decreasing, and as gradient is velocity, so we get that say that velocity is decreasing, which means that it is decelerating. Now this is actually a compound of all the sketches which we have discussed. And now if you label the points O to A, let's say this point over here is A and this point over here is O. Now from O to A, the gradient is zero, so the velocity is zero, so we can say that from O to A the object is at rest. Now from A to B, let's say, the gradient is increasing, so we can say that from A to B the body is accelerating. Now from B, let's label this point C. From B to C, the gradient is getting less steep and the gradient is decreasing actually. The curve is like this, like the curve is like this. So it means that the gradient is decreasing. So we can say that from B to C the car is decelerating. Now from C to D the case is a bit different from the cases which we have discussed earlier. Now here the displacement is decreasing. Now after an increase in displacement, if the displacement is decreasing, it means the distance from the initial point is decreasing, which means that it is coming closer to the initial point. That is possible if it is traveling towards the initial point. So from here we can say that from C to D the object is actually coming towards the initial point, and also if you see the gradient is actually increasing. So we could also say that it is accelerating towards the initial point. And here we're finished with the displacement time graph, and now let us move on to the next one, which is actually the velocity time graph. Now as the name says, velocity time graph is a graph in which velocity is plotted against time. So here on the y-axis would be velocity meters per second, and on the x-axis would be time in seconds. Now here we're going to be start off with let's start off with a straight horizontal line. This is a straight horizontal line and there is no change in the y, so the gradient would be 0. Now if we see, the gradient of a velocity time graph would be actually change in velocity over time, and if you remember, acceleration is what is actually change in velocity over time. So we can say that gradient of a velocity time graph actually represents acceleration. And as the gradient is 0, so here the acceleration is 0. And the velocity is at certain point any meter, so it would stay, let's say if it was 50, so the velocity will be constant at 50 throughout the time. If you see that this line's gradient remains same throughout the graph, so we can say that uniformly accelerating. Uniformly accelerating means that same increasing speed over same time period of time. So this line, now here it has a constant negative gradient, so it means that it has a constant deceleration, so we can say that the body is uniformly decelerating. Now if you look here, the velocity is actually increasing, the quantity on the y-axis is increasing with time, but the gradient is decreasing, which means that velocity is increasing and gradient represent acceleration, so acceleration is decreasing. So either we can say that, or we could also say that velocity is increasing at a decreasing rate. Both mean the same thing. Now here if you look, velocity is increasing but the gradient is also increasing. The line is getting steeper by time. So we can either say that velocity is increasing and acceleration is increasing, or we could say that velocity is increasing at an increasing rate. Now, a small part of this chapter is remaining, which is the acceleration of free fall and constant and terminal velocity. We would be looking at them in the next part. I hope you learned something from this video, and thanks for watching.